In this video, we're going to look at another example of moments in centroids. Let's extend the discussion of centroids to a flat plate, a lamina, with constant density rho formed by a continuous function f of x between x equals a, x equals b, and y equals 0. So our goal here is to develop formulas for the moment with respect to the y-axis, moment with respect to the x-axis, and the total mass of this region. And of course, we want to find the centroid, x bar and y bar. We begin our analysis with one of the rectangles. So we can see that xi bar, which is basically the center of mass of this, the x-coordinate of the center of mass of this rectangle, is simply going to be the average of the left-hand and right-hand points, 1/2 xi minus 1 plus xi. So the centroid of this rectangle is xi bar, and the y-coordinate is simply 1/2 of the y value, 1/2 f of xi bar. And delta x is equal to b minus a over n. So we're going to develop the formulas using Riemann sums. So delta mi is the mass of this rectangle, is simply going to be rho times f of xi bar times delta x. So density times the area of the rectangle. This is the mass of rectangle, ith rectangle. Let's call this Ri, R subscript I. Rectangle, Ri. And delta my, this is a moment of this rectangle about the y-axis, is going to be xi bar, the distance to the y-axis, which is given by xi bar, times the mass of this element, which is rho f of xi bar times delta x. So a key concept, the distance to the y-axis is going to be measured by the x-coordinate. So it's this distance from here to here. This is x, xi bar. There it is. All right, and basically the moment is mass times distance. This is the mass of this rectangle, and this is the distance of this rectangle to the y-axis, because we're finding the moment about the y-axis. So let's label this. This is the moment of this rectangle, the ith rectangle, moment of Ri about y-axis. All right, now let's find the moment about the x-axis. The moment about the x-axis is going to be rho f of xi bar delta x. This part is the mass times the average distance to the x-axis, which is measured by the y value. That's going to be 1/2 f of xi bar. So this is going to be the moment of Ri about the x-axis. All right. So the mass is going to be equal to the limit as n goes to infinity. We have infinite number of rectangles, I equals 1 to n, rho f of xi bar delta x. This is equal to, so the Riemann sum becomes a definite integral as we take the limit as n goes to infinity, integral a to b, rho f of x dx. Density times area. That gives you the mass. Now, the moment with respect to the x-axis. We sum up all the moments with respect to the x-axis. Limit, n goes to infinity. I goes from 1 to n. 1/2 f of xi bar times rho f of xi bar delta x. Key concept. This is the distance to the x-axis. This is distance. And moment is always mass times distance. Distance. And this part is the mass of the rectangle. This is equal to rho integral a to b 1/2 f of x all squared dx. Now let's find the moment with respect to the y-axis. This is limit n goes to infinity, I goes from 1 to n, xi bar, this is the distance to the y-axis, times rho f of xi bar delta x, and this is the mass of this rectangle. So let's label this. This is mass. And this is distance to the y-axis, distance. So this is the moment of one of these rectangles with respect to the y-axis. Now we sum up all the moments and take the limit. The Riemann sum becomes an integral. This is equal to rho integral a to b x f of x dx. So key concept, as n goes to infinity, xi bar approaches x. The discrete x values become continuous x. Delta x, the change in x, approaches dx. F of xi bar approaches f of x. The summation approaches the integral. And now we have developed the integral formulas for centroid of a plate. So mass is equal to rho times A, rho times area, rho times integral a to b, f of x dx. X bar is equal to moment with respect to the y-axis divided by the mass. This is equal to rho integral a to b, x f of x dx, divided by the mass, that's rho times the area, integral a to b, f of x dx. Y bar is the y coordinate of the center of mass is equal to the moment with respect to the x-axis divided by the mass. This is equal to rho integral a to b 1/2 f of x all squared divided by rho integral a to b f of x dx divided by the mass. Now notice something. Rho cancels out from the numerator and denominator. Rho cancels out. What does that mean? That means because the density cancels out, the center of mass is independent of the density. The center of mass does not depend on the constant density rho. It only depends on the geometry of the region. It only depends on the shape of the region that you have. All right. So let's find the center of mass of this region bounded by the graphs of y equals e to the x equals 0, x equals 1, and y equals 0, and the density is given as rho is equal to 2. All right, so we're going to apply the centroid formulas. Mass is equal to density times area, integral a to b, f of x dx. So the density is 2 times integral 0 to 1. These are the x limits of integration. E to the x, that's our function, dx. Integrating e to the x, what is the antiderivative of e to the x? Is itself. So we get 2 times e to the x, apply the fundamental theorem of calculus, evaluate from 0 to 1. So we get 2 times e to the 1 minus e to the 0. And we get 2 times e to the 1 is just e, and e to the 0 is 1, 2 times e minus 1. Now let's find the moment with respect to the y-axis. The moment with respect to the y-axis is rho, the density, times integral a to b, the distance to the y-axis, which is measured by x, times f of x dx. F of x dx, that's the area element, of course. This is equal to rho is 2, integral from 0 to 1, x e to the x dx. How do we evaluate this integral? What technique do we apply? Well, we apply integration by parts. We have a product of two functions, and substitution method will not work. Recall the formula is integral u dv. Integral for integration by parts is uv minus integral v du. And since it's a definite integral, we've got a to b, limits of integration, a to b here, and a to b. All right, let me put this in a little circle. All right, let's evaluate the moment with respect to the y-axis. So u is equal to x. du is equal to dx. dv, we'll let that be e to the x dx. and integrate both sides to obtain v. V is equal to e to the x. All right, so applying the formula, we get u times v. So moment with respect to the y-axis is equal to 2 times u times v, that's x e to the x, evaluated from 0 to 1, minus integral of v, which is e to the x, times du, which is equal to dx, from 0 to 1. So we get 2 times x e to the x, minus integral of e to the x is simply itself, e to the x, and evaluated from 0 to 1. We just tack on the limits at the end, easier to do it that way. So the moment with respect to the y-axis is equal to 2 times, applying fundamental theorem of calculus, put the upper limit in. Upper limit is 1 e to the 1 minus e to the 1. Put the lower limit in, 0 e to the 0 minus e to the 0. E to the 0, of course, is 1. So if we evaluate this, we get 2 times e minus e, that's just 0 minus 0 plus e to the 0 is 1. We get 2. The moment with respect to the y-axis is 2. What about the moment with respect to the x-axis? The moment with respect to the x-axis is 1/2 integral a to b rho times f of x all squared dx. So we get 1/2 times rho is 2, that's the density, integral from a to b from 0 to 1. F of x is e to the x all squared dx, and these 2's cancel out. We get integral from 0 to 1 e to the 2x dx. We're going to apply U substitution, let u equals 2x. So let me write this down here, but because I'm running out of space, I'll have to erase it afterwards. The u is equal to 2 dx. U substitution. We're going to apply U substitution to solve this. Let me now erase it and solve it in the little room that we have left here. So mx is equal to, what is the antiderivative of e to the 2x? That's e to the 2x. Divide by 2, reversing the chain rule or doing U substitution, evaluated from 0 to 1. So we get 1/2 times e squared minus e to the 0. E to the 0, of course, is 1. We get 1/2 times e squared minus 1. And this is the moment with respect to the x-axis. So summarizing, what we have is we solve for the mass. Mass is equal to 2 times e minus 1. We found the moment with respect to the y-axis. The moment with respect to the y-axis is equal to 2. That's what we calculated. And the moment with respect to the x-axis, we applied the integral formulas, and we obtained e squared minus 1 divided by 2. Now, x bar, the x-coordinate of the centroid, is equal to my divided by the mass. The moment with respect to the y-axis divided by the mass of the region. The moment with respect to y is 2. The mass is 2 times e minus 1. 2 cancels out, and we simply get 1 over e minus 1. This is x bar, the x-coordinate of center of mass. Y bar. Y bar is equal to mx divided by m. The moment with respect to the x-axis is e squared minus 1 divided by 2, divided by the mass. The mass is 2 times e minus 1. Well, we need to simplify this. We got 1/2 times 1/2. That gives us 1/4. We've got e squared minus 1 in the numerator. Let's factorize it as e minus 1, because that's difference of squares, e plus 1. So let me write that. A squared minus b squared, difference of squares. This is a minus b times a plus b. Divided by e minus 1. E minus 1, common factor cancels out. We simplify this, we get y bar is equal to e plus 1 divided by 4. So the centroid, x bar, y bar, is equal to the x-coordinate of center of mass. We found it to be 1 over e minus 1. And the y-coordinate is e plus 1 divided by 4. If we decimalize this, we get 0.58, 0.93. Now, does this answer make sense? Well, let's go back to the drawing that we have, the sketch of the function. That kind of makes sense, 0.58. So the x-coordinate of center of mass is 0.58. And the y-coordinate is 0.93. So somewhere in here, roughly about there, and that's reasonable. If you get an answer, for example, if the x-coordinate of center of mass was outside this region, we know something is wrong. So always check your answer, ask yourself, does it make physical sense? All right, thank you.